Hello there. During this session I'm going to consider the potential evolution of our universe. I'm going to introduce some terms such as critical mass and dark matter. So what do you think is going to happen to our universe? Okay. From what we know, we can work out there's three potential scenarios. Let me take you through those scenarios. The fates of an expanding universe are one. The universe is going to expand forever because there's not enough gravity and not enough mass to halt its expansion, and this is known as the open universe theory. Second theory, the universe will eventually start to contract due to the amount of matter and gravity causing it to close in on itself and have a final big crunch, and this is the closed universe. And the third model is that the universe will eventually find a steady state, which is a flat universe. And that requires a perfect balance between the kinetic energy of expansion and the gravitational energy trying to pull, or gravitational potential energy trying to close the universe. And this will require a certain density. The universe will have to have a certain critical density, and actually we can calculate what the density is going to be. We do that by doing some thinking. As I said, the total energy of the universe should be equal to the kinetic energy and the potential energy. So putting in our known formulas for these, and then adding the assumption that the mass of the universe is similar to that of a sphere of gas, so it's 4/3 pi r cubed times the density, and the velocity can be derived from Hubble's law. If we substitute these values in, and we recognize the critical density is when the kinetic energy is going to be equal to the potential energy, we can then say that half times the mass times the velocity is derived from Hubble's law squared equals g times 4/3 pi r cubed density critical times mass divided by r. The mass on either side cancels out, which is useful, and that tells us the critical density should be equal to a number which can be calculated from these constants. 3 times Hubble's constant squared divided by 8 pi multiplied with gravitational constant. So we've got a critical density. That's interesting enough, so we should be able to make a prediction about this. Observed universe density, let's see what it tells us. It is much less than the critical density, indicating there's not enough matter there. Yet scientists haven't given up on this idea of reaching a critical density. What they've done is they suggested that there's some dark matter, some matter which we can't observe, which should be incorporated. This could include three potentials: neutrinos, so these are particles of little mass produced in nuclear fusion, and there's lots of them out there. They don't really interact with something, so they could add to their mass. We have these things called machos, which are massive compact halo objects, and these are dim stars or black holes which are found in the halo of a galaxy, and they might have a mass between 0.01 mass of our sun and 1 mass of our sun. And also we have weakly interactive massive particles, which actually only exist in theory. So these are the ideas for dark matter. They all seem to be fairly out there, but why are scientists so convinced that there's some dark content to our universe which we can't see? Well, they have some evidence, as it happens. The evidence for dark matter comes from thinking about the mass of a mass near the center of a spiral galaxy, so a star of some sort. And if we look at that star and we think about its rotation around a massive center, we can think about the fact that the centripetal force should be equal to the gravitational attraction. So here we see gm m over r squared equals mv squared over r. Formulas which we've thought about beforehand. The mass of the star becomes irrelevant very, very quickly because that cancels out. And again, we'll use 4/3 pi r cubed divided times by the density to give us the general mass of the centre of the spiral galaxy. So therefore, the velocity should be equal to the square root of 4/3 pi density r. Okay, that's great. So we've got a number there. And what happens though is if we plot that number, the predicted number of orbital velocity drops away using that dashed line which you can see here, whilst the observed numbers are completely different to that, indicating that there must be more mass than we can actually observe. So this is one of the arguments for dark matter, and this is some of the arguments for why our universe isn't obviously going to be open. It could be flat or it could be closed. And these are some of the scenarios for what could happen with our universe. Maybe the end is nigh, maybe not. I'm sure scientists will spend a lot of time trying to work this out.